Hello. You're not smiling. You're not smiling. Okay. Hello, Wishi. Hello, Gabriella. Hello, Stephanie, Michaela, Alyssa, Vivian, Jayla, Catherine. That's the visuals now. Hello. Oh, wait, more people. Hold on. That was the visuals. Now the textuals. Good afternoon, Alyssa. Good afternoon, Andrew. Good afternoon, Vivian. Hello and good afternoon, Wishi. Good afternoon, Catherine with an E. Good afternoon, Gabriella with a Yi. Hi, Michaela. Good afternoon, Jayla with a prof. Good afternoon, Stephanie. Good afternoon. Whoa, I can't accept that, but I will. Thank you. No, good afternoon, Nicholas. Whoa. Okay, I can't. Yeah. I mean, thank you. I'm still trying to catch up to what that carrot means. Anyway, I mean, I get it, but okay, you were too kind, and I can't accept that. And I'm not telling Walters. I'm totally telling Walters. Hold on. Okay. Oh, and now you're smart. Think I don't see that? Okay, that's cool. Okay. Who else? Oh, and more people coming, more people coming. Okay. Whoa. Okay, I see. I have to pretend I'm not reading those because I just passed the smelling salts. Good afternoon, Mark. Good afternoon, Warda. Good afternoon, Lakshmi. Awesome. Okay, oh, no. Yeah, okay, that one, the last thing, Gabrielle, okay, I'm gonna just deal with that one in private. Like, I'm freaked out by that. Oh my God, that's so funny. Okay. You know, you made me nervous with that whole thing, Gabrielle. Anyway, okay. Yeah. See, now you're gonna distract me. Okay. Okay, there's only one way for me to get back on track here, and that's that. Oh my God. All right. I'm totally pretending to not know what's going on right now. But I did tell you guys. Yes. Oh my God. All right. I'm totally, no, he does. But you all know I have, okay. Oh my God. Okay. Stop killing me. Do you all know, I told you this isn't, I have told you, right? I told you that I literally read his first lab report for physics 203 that he wrote as a student. I've told you that where I read that out loud, right? Or yeah, I did. Okay. Yes. Okay. So I'm not gonna go down that road again. Okay. Okay. You're all killing me. Okay. Let's do some fin. Well, you know what? Oh my God. Wait, he has a Twitch? Okay, I'm totally not reading this. At least, look, I'll say this though, at least the man does know how to, wait, Twitch. Does he actually have a Twitch stream? Should I even ask that? I totally know that he knows how to navigate Discord, which is more than I can say for myself. Does he actually? Okay, okay, stop. I told you they didn't invent this ADHD diagnosis until I was like 20, right? I mean, that's not really true, but okay. We have to do physics. What did I say? First twin. Does he? Yeah, I guess I should ask him. I did not know that actually. No, I aspire to be him. Remember, God, you guys are killing me. If he really aspired to be me, he would stay working with. You might be. He has. Okay. All right. Now we're gonna. Thank you. We're gonna stop. We should all aspire to be him. And I think my wife wishes that I had his beard. Okay. Anyway. Oh, okay. Thank God, people are coming. That'll help. Okay. Okay. We are really okay. Okay. We have to do physics, but you know, here's what I am gonna do though, because we are in this mode and everything, and apparently I can't my writing skills. Okay, now I don't even know what we're talking about. Okay. Thank you. You're all very too kind. Here's how we're going to shift gears here, because I clearly cannot just like drop physics on you now in this book, but you're going to drop physics on me. What is on the bottom of the screen? Wait, what is on the bottom of the screen? Oh, you wait, like the whiteboard? The stupid. Oh my God. Okay, you're totally killing me. You know what it's actually supposed to be? Well, oh, that makes sense. Okay, fine. We'll go with that. Like, that is not what okay, yes, it's yeah. Oh my God. I will try to explain those drawings someday. I mean, of course they have something to do with me, but like I'm many things, but I'm not actually bald. So it's not literally me, but okay. But here's what I do want to talk about, all of you. You know what I do? Oh my God. Wait, the numbers are. Oh, maybe I should quickly explain that. Actually, wait, honestly, because I mean, some of you I've now had 2 semesters, and if I've never explained the numbers at the top, is possibly worth. I'll just quickly. I mean, there's a lot of significance. I could go on for months. I mean, no joke. I could go on for months as to why I do the numbers on the top and like what I think the many layers of their significance is. But just directly speaking, so getting slightly serious here, directly speaking, the numbers at the top of the screen right now, and I'm talking to everybody now, like I know we're joking around and that is like a kind of a joke question, but yes, every day I put those numbers on the top, right? And I will say this too, like, well, I think you might have even seen in lab. I mean, I've been putting those on the top of whatever my physical whiteboard is in class. Like this is totally not a COVID Zoom thing. Like I put those numbers on the board. I've been putting those on the board every single day that I teach, for almost since I've begun teaching. Like that is not a COVID Zoom thing. That is something that, and in fact, whenever I write letters to people or cards to people or something, I always put, so just so you know, and I'm sure some of you have figured it out or realized it, but I mean, of course, that's the phase of the moon. So I'm talking to everybody now. This is not like a serious point, like it's not on your exam or something, but it is a noteworthy point. Like in terms of like what all that stuff is at the top of the whiteboard every Zoom class, all the way to the right. I mean, first of all, yes, that's the phase of the moon. I would imagine most of you recognize that. And the black part is the black part, like, or actually, no, am I backwards? No, I think I'm not. Am I backwards? It gets confusing because, yeah, no, it's not backwards. Like that is a waxing gibbous moon. That is to say the moon is almost full. Like it is growing and it's almost full. That's what that is. But then the RST, and again, I know that many of you have figured this out or take this for granted, but it's true also that I probably never explicitly said. RST, R stands for sunrise, S stands for sunset, and T stands for temperature. So it's the time that the sun is rising today, supposedly, the time that the sun is setting today, supposedly, and then the sort of the high temperature for today. Now, those are 3 very different types. Well, that's 2 very different types of numbers. Like sunrise time and sunset time are, in some ways, very precise and very specific numbers. They're also very location specific. Honestly, the rise and the set time that I put there when we have Zoom class together, like honestly, that's the sunrise time and the sunset time in Maine, where I'm broadcasting from. I've noticed every time I come to New York, every Tuesday I come to New York and I do that, like, actually, it's kind of wild how different the sunrise time and sunset time. Like if you look it up right now on your phones or whatever, you're going to find that your sunrise time is somewhere in the 7s, and so is your sunset time. Like there's like a 10-minute difference between Maine and New York, which is actually kind of staggering to me. But and I'm not trying to get all off the subject, or I'm not trying to let you all get me all off the subject, but I have, in fact, I was going to say, I could teach a whole class in just the significance of those 2 numbers, or like why I do it, or why I care, or what it means to track them, and blah, blah, blah. I actually have taught whole classes in that, meaning astronomy classes. We're not going to get all into that right now, but that is what they are. Supposedly, like that time that I put there is the time that the sun rose this morning, in Maine. The set is the time that the sun will set tonight in Maine. The temperature is the high temperature today in Maine, just because like that's where I am. Sorry. And I will argue, let me say this, I'm not even looking at the chat yet. I will look in the chat in a second. Of course, this is slightly off the topic, but I've always been doing that. There's many reasons I do that. Some of them are strictly scientific. Some of them are maybe more spiritual. But one thing, as long as somebody is asking right now, one thing about those numbers, let me tell you, since you are physics 204, something about those numbers that one cannot actually appreciate until it's physics 204 is, if you took any of those numbers, not any, if you took, I'm intentionally not looking at the chat for a second, just so I can sort of make this into a serious point. The sunrise and sunset time, right? I'm can I say this concisely? I think you all know that, as we're heading towards spring, every day the sun rises a little bit earlier and every day the sun sets a little bit later, right? I mean, and that will continue to be true all the way until the first day of summer, the summer solstice, and then the days will start getting shorter again, right? And then they get longer and then shorter, blah, blah, blah. And this has nothing to do, I'm not even talking about daylight saving time or anything like that. But, the natural rhythm of the day is that the amount of sunlight we get is greater through winter and spring. And then the amount of daylight we get is lesser through summer and fall, and back and forth, where, well, I bet you see where I'm going with this. And you're right. If you were to make a graph, and I'm telling this to everybody right now, if you were to make a graph where on the horizontal axis, you plotted day of year, like the date, right? And then on the vertical axis, you plotted, say, minutes of daylight in the given day, something like that, like total minutes of daylight in a given day, and you were to make that graph, I bet you know what kind of graph it would be. I'm sure you can guess, and I would say put it in the chat, except I'm intentionally not looking at the chat for a moment. Like, oh yes, it would definitely be a cosine graph. Oh yes, the amount of daylight per day absolutely oscillates harmonically. Wah, wah, boom, 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 boom. Like for real. Similarly, if you were to make a graph of the percentage of moon disk illuminated as a function of day, right? Like if you were to put date on the horizontal axis and plot percentage of moon disk illuminated on the y-axis, right? Like a full moon is like 100%, a new moon is like 0%, a half moon, or what some people call like a first quarter moon or a third quarter moon, like that's 50%, et cetera, et cetera. A crescent would be, right? If you were to plot the percentage of moon disk illuminated as a function of date, you would get a cosine graph. You would get harmonic oscillation, i.e. you'd get an angular frequency that would be constant and independent of amplitude, blah, 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 blah. Like for real. Like basically, what if you think what I'm saying to you, this is what I'm saying to you. Now that you're aware of harmonic oscillation, and now that you're aware of the math of it and the differential equation and the properties and the features and the fact that harmonic oscillation doesn't just mean oscillation, it means oscillation that is so steady that its angular frequency, its cycling rate, is independent of its amplitude, right? Like that's ultimately what harmonic oscillation means, and ultimately means can be plotted with a cosine function, da, 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 da. I'm telling you right now, anytime, the next time you come across any phenomenon in nature that seems at all cyclical and reliable and dependable, chances are extremely high that what it is literally a cosine function, a harmonic oscillation. Harmonic is that it's so regular and so constant, yet at the same time, it's just the simplest, smoothest way that something could go back and forth and back and forth. It's really regular, it's really constant, it's really reliable, harmonic oscillation. So you almost would think it'd be too perfect ever to like really arise. But the flip side, now I'm babbling, sorry, someone accidentally got me into physics, oh well, even though it's so regular and so reliable and so definite that we make clocks out of it, that we have this precise mathematics to describe it, et cetera. At the same time, all harmonic oscillation really is, if you think about it, is up and down or back and forth motion that is smooth, that is smooth, that is continuous, right? In other words, something that would go back and forth in nature, such as the cycles of the day or the cycles of the moon or whatever, they couldn't, we've said this before, they couldn't go like this in nature, right? Because in nature, you can't skip. In nature, in macrocosmic observable space and time, you can't skip from 1 mile an hour to 3 miles an hour without passing through 2 miles an hour, right? And you can't pass from 1 inch to 3 inches without passing through 2 inches, which means if you really think about it, since you can't be discontinuous in macroscopic nature, if a position function can't be discontinuous in nature, and if a velocity function of some phenomenon can't be discontinuous in nature, then that means that the derivative of it can't be discontinuous in nature. That means not only can we not have jumps in nature, but we can't have corners or jaggeds or straight lines in the graph in nature. So anything in nature that actually cycles back and forth has to do it in a way that's smooth. And what that automatically ends up meaning is it has to do it in a way that's infinitely smooth, like smooth to all of its infinite derivatives. That means it has to actually be like a cosine function or a sine function. That means anytime you ever observe anything in nature that seems regular and cyclical, it's probably not just cyclical, it's probably freaking harmonic. Okay, so part of the reason, I know I'm like totally off on a tear here, but I'm glad someone actually asked after 2 semesters. One of the reasons that I plot this data every single day, just casually, the sunrise time, the sunset time, and the phase of the moon, is just that without ever asking you to consciously do anything with it, without ever asking us to consciously be examined on it or make a graph of it or anything, we're just letting data sink into our system that together makes a harmonic function. This is where physics came from in the first place, was people casually observing these phenomena in nature, taking this data in nature because they either needed to or wanted to, and then seeing these patterns like as a natural relationship to nature. So good question is what I'm saying. Okay, so that's part of, there's other reasons I do it too, but that's what that is. The RST is sunrise time, sunset time, temperature, and the sunrise and sunset, and then it's phase of the moon. And those three things are just natural harmonic oscillations right there that we're living and breathing. The temperature is crazy. The temperature is a totally other thing. I'm going to look in the chat for a sec. Sorry, I'm totally, but that was a good question. That is, I'm going to get to physics now, or that was, wait, oh my God. Okay, wait. Okay, wait, I'm not going to read this out. I'm just reading this to myself. Oh, cool. Oh, okay. I'm reading the chat, but I'm reading it to myself. Weather forecast. No, hardly. Oh, no, they're not textbook sessions. No, they're totally okay. Bring a lobster. Okay. Yeah, me and lobster. That's funny. Okay, this is a thing. Must be written. You think I'm driving all the way to New York? Please. Okay, I'm usually on a bus. Mike, okay, that's funny. Okay, I'm totally saying I'm not reading this out loud, but I am. No, the whole year is one big harmonic oscillator. That is true. That's what the cycles of season. Okay, he doesn't. Oh, well, our signs get okay. Yes. Okay. You guys are very, very funny. Okay, I'm trying to resist. You are very funny and you're very kind. And you're very right. Most and those of you who are saying anything true. And gas prices are crazy. And I don't drive the whole way. I was doing that first semester, but I couldn't. Driving all the way to New York on Tuesdays actually first semester meant that all the rest of the week I was recovering, like literally I couldn't. But anyway, okay. Okay. What are we doing now? So we and why are my glasses off? I don't know. Okay, here's what we're gonna do though. Well, wait, sorry. No, okay. Yes, we're gonna go back to sorry. No, yes. Okay. I had to make a decision there. Okay. I'm going to take a risk here, but you know what I would like to do? I would actually like to ask you feedback. I heard my own personal things, but I want to hear from you, content wise, like material wise, not like social commentary, but material wise. One of the last things that I think Professor Johnson sort of asked you to do or think about at the end of yesterday was like keep track of or consider things that are coming up in the lab or that you're being asked to consider in the lab that have not yet been addressed directly in lecture. And let me say, before we go any further, there definitely are such things. And it's not an oversight. Like I know what they are. I mean, I know some of them. I know very specific things that definitely are supposed to be happening in the lab that have not yet happened in the lecture. And that's, again, that it's not that that's a mistake or that should be a problem, but I would be interested in hearing from you. So I'm going to turn it to you guys now. We're going to try to sort of have a discussion here, and you can use the chat or you can talk, but I would sort of like to hear your perspective on things that you think are beginning to come up in lab or things that you think you're sort of learning or trying to learn or whatever in lab that have not yet been raised in lecture. In other words, this is also an opportunity that you can ask questions about things that you don't understand. That would be totally fine. Or you could say things that you think you are understanding. That would also be fine. It's not, I'm not asking for like, oh, and then I didn't like this part of lab, or, and then my lab partner hit me and then like I cried, or you know, I wish Professor Johnson was taller, or like whatever. It's not like that. I'm not looking for that right now, but I am looking for just like, okay, let's share and care, like what kind of is going on in lab physics wise, and what can I want to use this period, this time to start trying to bring the lecture material a little closer in alignment to what you're doing in lab. So I'm turning it to you. I mean, it's a risk in this room, I know, but I turn it to you to tell me either vocally or in the chat, like this is a time to raise it, because at some point some work is going to be due in lab, of course. So this would also, okay, question. Okay, here we go. This is good. Okay, fair enough. By the way, so Nicholas is saying in the chat, question 11 in the lab didn't make sense to me. That's a fair place to start. That's the type of thing I would like to hear. Only I have to admit, I don't remember what question 11 is. So could you be a little bit more specific? But yeah, I'll try, depending on what it is, I'll try to address it right now. And I will put my glasses on. But so question, or maybe, yeah, question 11. I mean, I could look it up, but it would help. Maybe he's typing. Okay. Or maybe somebody else remembers what Nicholas said. Question 11, or, oh, here we go, here. Oh, whoa, wow, okay. Oh, here he goes. Oh, so he was, okay. Oh yeah, and I heard, yes, no, good. I'm glad that Johnson was totally poker facing you. Yes, I have heard that he was not answering questions, which is good. That's what he's supposed to do. We pay top dollar for people that can't answer questions, as you know. No, I mean, seriously, that's good. But now, okay, I'm looking at the question that Nicholas wrote. The team is up. Oh, actually, I must admit, I mean, I'm excited about all of you. I mean, I do love this group, as you know. I do have to admit, this question that Nicholas has chosen to put in the chat here, and it doesn't have to be the only one, and don't let it stop others of you from putting in whatever you want to put in. But I will say this is a perfect example of something I would love to go over. I mean, I would anyway, but I would absolutely love to address this and will. I'm just looking. Yeah. Can I get a refund? Part C, really? Wait. Oh, okay. Let me say this. And again, don't let me stop others of you from putting in things about poker. I mean, putting in things about the lab. But I will say, indeed, if I had to pick one thing to do, if you didn't say anything, I mean, if you hadn't said anything, I do have to admit that this question that Nicholas is putting in, 11, A, B, and C, and yes, indeed, particularly C, and I do see that. Oh, yeah, that is the point of the lab. It doesn't mean it's obvious. I don't think that it should have been obvious. I'm not saying that. But if I had to pick like the punchline or pick like the central nugget for me to address with you guys, it certainly would be that. So I am delighted to. So if nothing else, when I start addressing this 11 ABC thing in a moment, let me assure all of you that is not me being off the topic or just like answering a side question of Nicholas's or something like that. Like, oh, indeed, that is the point. That would be the lecture. So I will address that in a moment. Let me just see what else you put in the chat just to make sure. And I'm going to try. He was gaslighting. I heard he even told me that you told him that he was gaslighting. That's hilarious, even though I hate that word. But yeah, that is what he's supposed to do, honestly. But okay, wait. Oh, and I see what's in the direct chat. Wavelength and phase velocity. Okay, fair enough. And yes, that's important too. And we will get, he can't, and I will get to that. And the gaslighting isn't even the word. Exactly. Ha! Wow, he's good. That's funny. That's funny. Okay. Oh, yeah. And by the way, oh, yeah, he could throw me under that bus. First of all, I'm born. I am the bus. Are you kidding me? Like, I did tell him to keep you there. You have no idea. No, that is one thing I'm completely outrageous at. Like, you are supposed to stay to the end. I'll totally take response. And I know that there's been a lot of periods this year in a lot of classes where people have not stayed to the end. And that's because this is like a messed up, because physics is in chaos right now due to COVID and everything else. But, oh, even in my least strict, most pushover days, though I do make people stay to the end. Freaking it's lab, yes. But okay. But no, I am the bus. Yeah, but I'm gonna pop his tires. It's funny. I mean, the bus that, and in fact, it's a Flix bus. How do you think I get to New York every Monday night? But okay. So I'm gonna do this thing though, even if I don't finish now because of all this messing around. It's funny. Okay. I like how Jayla's totally involved in this too. Go, Jayla. You get like extra points just for being you. Not like the other people don't, but yeah, no, Jayla's like on fire today. Don't think I'm not noticing. Okay, in a good way. All right, I want to address this thing that Nick, okay, so back to material at least for a moment. And again, though, if you have serious things about life, you can keep them coming too, even if I don't get to them today. But, and the ultimate thing I want to get to is, in fact, sort of this thing that's written right here on the page. But here, yes, okay. Okay. So I want to explain something about, so we're going to go back to some differentiating here, some derivative stuff as it applies specifically to what you're doing in the lab, or even better, as it applies specifically to the thing that we're developing in lecture the last Monday and the last Wednesday. Remember, in lecture, what we've been talking about is not just one oscillator, but a whole group of oscillators that are all laid out and are all staggered in phase, right? In lecture, we've been talking about developing an equation that applies to this collection of phase staggered oscillators, right? That's what we've been doing in lecture. And in lab, what you've been looking at is a wave pulse. Now, I'm ultimately here to argue that they are one and the same thing. That is definitely an underlying lesson in all of this, okay? And I'm ultimately here to argue that a collection of phase staggered oscillators and a wave pulse can be described by the same mathematics, which is some kind of y as a function of x and t. Okay, that is ultimately like a big thing that's going on here. But I want to back up, and we're going to take a bunch of derivatives to look at that. But I want to back up and say something about derivatives here. Again, this is all to answer Nicholas's question or to answer question 11 in the lab or whatever. I want to remind you that if you have just any arbitrary variable, z, call it z. Z stands for just like some variable in math or physics, right? If you write down delta z, we've said this before, but let's remind ourselves, when you write down delta z, you might say that means change in z, and that's true. But what I like better is to view the delta as meaning difference in z, subtle distinction. But I like to think that when we write down delta z in math or physics, what we really mean is a difference between two values of z, and specifically what we mean, what we specifically mean is a small but finite difference between two values of z. That's what we mean when we write down delta z. As in delta y means y2 minus y1 as in rise. And then delta x means x2 minus x1 as in run. And when we use the delta to mean it could be a small difference between two values, but it's big enough that we literally can measure it, we can picture it, and we literally can subtract one value from the other and say that's our difference. We use delta when we mean that the two values actually are distinct from each other. But then we switch to D, right? We switch to D when we go to the limit, right? Technically, really, and if you have room on the page, well, yeah, let's in fact, right? Like dz equals really the limit of delta z as it's really the limit of delta z as delta z approaches zero. That is to say, dz is what we write down when we mean an infinitesimal difference between two values. I know, talk about infinitesimal, my handwriting here is, but right. So technically right now I'm reminding you, but now I'm going to go a step further in a moment. But technically I'm reminding you that we use delta z when we mean a finite difference between two values of z. Then we switch when we go to the limit, when the two values of z are so close that they're so close that they are arbitrarily close, we switch to dz. So dz is the infinitesimal difference between two values of z. We call dz a differential, right? Now, technically, dz is not a derivative. It's a differential, as in dy is a differential. It's like a differential rise, and dx is a differential. It's a differential run. And you put dy over dx, and you get infinitesimal rise per infinitesimal run. And that whole package is called a derivative, right? An infinitesimal rate of change. Right now, again, technically or in principle, you know this already. I'm just reminding you of notation that we use. Now I'm going to introduce a new piece of notation, new to this class, or at least to lecture. I'm going to say from here on in, if we switch from dz to this thing that sort of looks like a lowercase delta, kind of, but it actually really looks like some sort of Celtic letter or something that I don't know what it's called. We're going to switch to this, and this is new. I'm teaching you this right now. When we switch to that, what we mean is an infinitesimal, what we're going to mean from now on is an infinitesimal difference between two values of z, just like before, assuming, now here's the thing, we're going to use this new symbol, this new type of infinitesimal, when z assuming dependence on more than, okay, I'm going to read, this is obviously illegible. I'm going to read this out loud, and then I am actually going to rewrite it on the next page. I know this is illegible. What I'm writing is, we use that funny symbol, a symbol that we're going to call from now on the partial. That funny symbol z, partial z, is what we're going to use from now on when we mean an infinitesimal difference between two values of z, assuming that we're in a context or a situation in which the function z is depending on more than one variable. We're going to use this partial symbol. Again, I'm going to write this on the next page, so just listen for a moment. We're going to use this partial symbol from here on in when we have a function of more than one independent variable. This sounds like I'm just talking about something off the topic, but it's totally to bring it back. This is all about the question that Nicholas is asking. Honestly, it's all about question 11 from the lab. So let me write this on the next page. So I'll just read it again in case you're trying to copy. So partial z from now on, triple equal sign equals infinitesimal difference between two values of z, assuming a dependence on more than one variable. So I'm going to write this on the next page now. Okay. Okay. Again, this is mathematical background now that I'm teaching you right now. I'm teaching you mathematical notation for a mathematical concept a mathematical concept that you've had in your mind all the while, no matter what. But now I'm giving you notation for it to nail it down and to make it easier for you to understand question 11 and to answer it and to relate it to waves and all that. Here's what I'm saying. I'm saying for the first time in our lives, mathematically and physically, for the first time in our mathematical or scientific careers here, we're being asked to explicitly face a situation where we have a function of more than one independent variable. Now, I am saying for the first time in our lives, I'm not trying to be dramatic, but I'm saying up until now, it's been very deliberate and on purpose and conscious that whenever we've said function up until now, like in any math class we've taken or in any science class, we very on purpose have always meant input, output. You put one number in, you get a number out. Every function we've ever looked at has literally been a single varied function. Input, output, cause, effect, independence, dependence, right? And that's why, by the way, every single lab you've ever done in a science class until now on purpose could be turned into a graph, because a graph is always, we tweak, or like Mark says, like I choose one measurement to vary and I hold everything else still. I tweak one thing and then nature responds by tweaking something else. So I play with some input, some independent variable, and then nature responds in some output, some dependent variable. So, and then we try to figure out what that function or that relation is in every math class or every science class until now. And then we can turn it into a graph, whatever our result is, because we have input and we have output, right? That's on purpose and the real deal in math and science to this point. Now, for the first time in lab, you're looking at a phenomenon. You're looking at a phenomenon where, in fact, the output, the dependent variable, actually is a result of two independent inputs. This is actually a big deal. This is one of the reasons that we spent 2 weeks on lab 3 at least. And one of the reasons that if you're having any confusion at all or anything seems weird, there's a reason. Oh, this is a big step. It's not an undoable step, but it is an interesting step. And by the way, this is a reason why, even though you just like took this simple movie last week in lab 3 and then it just like, well, didn't seem that big a deal, but then you had to produce 2 different graphs from that same movie. Think about it. The reason, but both of those graphs had the same output, the same dependent axis called Y, because we're now for the first time looking at a phenomenon where the output, i.e. vertical position, the dependent thing that we're ultimately looking at, like how high is the phenomenon, how high is the metal on the, like on some vertical axis. What we're saying is that in this phenomenon of pulses going back and forth on a string, the height of the spring is actually dependent on both time that you look and horizontal position that you look at, right? We're saying that in the case of the lab, Y is a function of X and T, both at the same time. It's independently a function of X and it's independently a function of T. T are both independent variables, which, let me stress even further, they're both independent variables partly in the sense that Mark said like weeks ago, like they're both the variables that we tweak. And how do we tweak them, by the way? It's not that we like play with another, but we decide when or where to look, right? Like we tweak them by taking our data either at a specific X spot or at a particular moment in time, i.e. a particular frame of the movie, right? So we choose our X and or we choose our T, and from that we find a Y. So number one, X and T are independent in that sense, like that Mark said, but also they're independent in that they're independent of each other, right? X does not affect T and T doesn't affect X. X is not an output of anything. T is not an output of it. They are both independent inputs into this overall output we get out called Y. Okay, that's what's going on in lab 3. Now that motivates some new thoughts. And so first of all, you can't capture that whole phenomenon in one graph. You had to have two independent graphs, two independent functions, two independent cosine functions, one of time, one of space. One thing that we're ultimately saying in lab 3 is that you could put those two cosine functions together in what's called a superposition and write them as one big cosine function of t and x at the same time. Like that is one thing we're saying in lab 3. But then that raises a question: how do we deal with such functions? How do we deal with functions of more than one variable? Let me say again, I'm here to teach this. This is what we're here to discuss. This is why I like the fact that Nicholas raised question 11. This is not obvious at all. And let me please say again, like it's totally learnable, it's totally teachable. It's here what we're here to do. It's part of our curriculum. But don't think for a minute that I'm assuming that you've seen this before. In fact, I'd rather think that you had not. We have not ever discussed this in a math class or a science class before. We almost wouldn't want to because it almost seems too hard, except that the physics is staring us in the face and saying, hi, I'm a function of more than one variable, I being a wave pulse. So I'm stepping back and saying, okay, if we have a function of more than one variable, if rise in some function is actually depending on two different kinds of runs, right? Like what do we do? Can we take derivatives? Can we look at rates of change? The answer is yes, we can. We can take derivatives one at a time. Just like in the lab, you can look at one variable at a time. In the lab, right, you can hold x constant, like you can pick one position, one horizontal position in your wave pulse, and then just play with t, i.e. advanced frames in your movie, and see how y is affected, right? So you can hold x constant and play with t as you're investigating lab data. Or similarly, you can hold t constant, i.e. you can pick one frame of your movie, just stare at it, and then let your eyes gaze across from left to right and see how y varies as a function of x, right? In the lab, you can hold one independent variable constant sort of temporarily or provisionally while you play with the other. Well, we can do the same thing in calculus. What we could say is if we have a function of more than one independent variable, we can look at how the dependent variable changes with respect to one independent variable at a time. We can take the derivative. So I'm now talking in general math terms here on this page right now. No, I'm talking about just like z as a function of x and y. So just any general function of more than one variable. It's not just specifically about the lab. There's no t in here, right? I'm just being general for a moment. I'm saying in math, if you have some function of x and y, and you call that output z, then the rise in z, the infinitesimal rise in z, is the sum of what we call the partial derivatives, the partial rise. It's like, we're going to say from now on, we're going to write that squiggly new d symbol. It's called partial. We're going to write partial z over partial x to mean like this thing right here that I'm looking at. This means the rate at which z changes with respect to x. It's like if you move along the x-axis, what happens to z? Assuming that you held y constant. Okay, so dz dx, or like partial z partial x, means the rate of change of z with just respect to x, treating y as a constant for the moment. This is the mathematical version of what you do in the lab when you look at one rate of change and you hold the other thing steady.
Professor Averball?
Yeah, sorry. Yeah. Sorry.
So like, for example, can you say the part of the equation is where dz over dx, that's the part where it's like one screenshot, and then dz over dy is the part where it's the actual video?
Totes.
Okay.
Yes, that's awesome. And like, please give yourself 85,000 class participate. That was video, that was voice, that was a totally on point question. Yes, it's like totally yes. So let me go straight to that. What's on the page right now is just like my general mathematical point. And basically what's on the page right now is just my way of saying in math, we're allowed to do exactly what you were doing in the lab. So now, yes, let me do that. Like, so what he's saying, so just in sum then, to take a partial derivative is to take a derivative of a function, is to take a derivative of a multivariable function, but it's to take one derivative at a time. So yes, to relate it to the lab right here, for example, okay, so yeah, no, totally great question. And I am watching the time. So I'm going to do now, I'm not trying to give away the whole farm, but yeah, let's go to the lab. So in the lab situation, let's say we have this equation, y equals a cosine omega t plus kx, which is like a superposition of the cosine of t and the cosine of x put together in one equation. So I have one equation, and this is also, by the way, this equation, I hope you see, you could think of this as having ultimately come from the lab 3, or you could think of it as having come from the lecture material where we set up a collection of phase staggered oscillators. I'm ultimately trying to argue that they're one and the same. But anyway, whichever way you think of it, if you look at this, so I'm talking to everybody. I'm not just talking to Mark, although again, Mark's follow-up is a perfect follow-up to Nicholas's original question, but this is the lecture no matter what. If you look at that equation, y equals a cosine omega t plus kx, like yes, I'm getting that from physics, but like, let's just look at it mathematically for a second. That would be an example of some equation for which y is a function of both x and t. Like x and t are the independent variables here, right? And a, omega, and k, those are all constants, right? So what I'm saying we can do, calculus-wise, we can literally take, and this is now what question 11 is asking you to do, okay? You could take something called a partial derivative. And by the way, I know you didn't know this notation. Like, I understand that I'm telling you this notation now for the first time, you meaning everybody in the room. You didn't necessarily know this notation yesterday when you were in the lab. Like, you think, but whether you use this notation or not, I think many of you would see the concept, or did see the concept that I'm about to say. I'm saying I can take the derivative of y with respect to t. What that means is treat everything else, including x, treat everything else as a constant, because they are, but treat x as a temporary constant. I'm about to look at the rate of change of y with respect to t, holding x constant. In other words, I'm mathematically about to do exactly what Mark just said. I'm going to just like pick an x value. I'm just going to think about some x value in my movie and let the movie run, let the frames run, and see what happens to y. Well, mathematically, that means going like this. It means going right. You see what I did? I'm doing partial y, partial t, meaning I just differentiated. And this is the part I do think you could have done in the lab yesterday, whether you knew all this notation or not. I'm just asking you to take the derivative of that function with respect to t. Treat t as the variable, treat everything else as a constant. So what I'm very explicitly telling everybody, and again, I don't care if you got it yesterday or you're getting it now for the first time. I'm just saying to everybody, notice that I took the omega out, like I chain ruled the omega, but I did not take the k out, because for the moment, I'm treating x as a constant. Why am I treating x as a constant? Because I'm doing partial y, partial t. I'm looking at the partial rate of change of y with respect only to t. If I were to do this again, so I'm going to do it one more time. If I were to do the second partial derivative of y with respect to t, I would just do the same thing again. I'm going to go like this. right? So in this, and I'm looking at the time, oh, this is perfect. Okay, this really, I am glad you guys are totally saying and asking the right things, honestly. I'm gonna hold this thought for a minute. This would be the second partial derivative of y with respect to t. So I took two derivatives of that expression, treating t as the variable, leaving the kx thing alone like just as a constant. I'm treating it like it was just a number or like phi or something. Now I'm going to turn the page, and now I'm going to do the other derivatives, which question 11 also asks, right? Now I'm going to turn the page and just reminding, I'm continuing. So the function is still y equals a cosine omega t plus kx. Now I'm going to take, I know I'm being inconsistent with the colors, but now I'm going to, Now I'm going to take partial y, partial x, okay? So now I'm explicitly delineating to myself, okay, now I'm going to treat x as the independent variable, and I'm going to hold t constant. Again, this is the mathematical equivalent of sitting there and looking at your data like the way you did. So I'm going to take one derivative with respect to x. I'm going to get negative a k sine omega t plus kx. Everybody understand, right? I mean, stop me if you don't understand, but you see what I'm doing? Like now I'm treating t as just a constant. And again, you might ask, well, how did you know why t? Well, because it says x in the denominator of my partial derivative. So this is a partial derivative. It's the rate of change of y with respect to x. It is not treating t as a variable. It's treating it as a constant. This is what partial derivative means. It means this. And this is all allowed. The assumption, the thing I wrote in general like 2 pages ago is just saying the full derivative of something is the sum of the partial derivatives. We're assuming that the total rise in a function is this. We're not assuming, we're believing, we're asserting. 2 pages ago, what I wrote down was if you have a function of more than one variable, the rise in that function is the sum of its rate of its derivative with respect to one of the runs times the run plus the derivative with respect to the other runs times that run. It's just saying that the total rise is the sum of the rise runs. Anyway, you can look at that again in a second, but this whole thing is just assuming that the whole is equal to the sum of its parts. So we're looking at one part at a time, believing that they would all go together to make the whole. So I take another derivative now. I'm going to take another derivative. Now, why am I taking 2 derivatives? I'm always interested in 2 derivatives, ultimately because f equals ma, and a is the second derivative. Like all physics is all concerned with second derivatives. So I do this again, and I get negative a k squared cosine omega t plus kx, right? Just chain rule again. So this looks, so it's like very much, I'm just doing the same procedure that we did for harmonic oscillation a week or 2 weeks ago. I've taken 2 derivatives now of our expression, only I've done it twice. I've taken 2 derivatives twice, one for time and one for horizontal space. Now, in principle, I believe what I've just done is answered question part A and part B of question 11 of Nicholas's question. But luckily for me, we have 15 minutes left and we still have part C. And part C I'm going to do right now. I'm going to do it for all of you if we're all still here together, because it's the point. I'm saying that, okay, so I'm saying, okay, did I do this right? Yeah. So now look, right now, we haven't proven anything. We haven't like finished anything, but we've got some things here. We've got the second partial derivative of y with respect to x equals negative a k squared cosine blah, blah, blah. And then we have second partial derivative of y with respect to t equals negative a omega squared cosine blah, blah, blah. two different derivatives, one of space, one of time, but of the same function, two very similar but different answers. Similar but different. They're so similar. I feel compelled to see if they're related in some way or to try to relate them. This is, again, this is now question 11C. It says like relate those two results to each other. Well, I feel like I can relate them to each other because they're both very related. They're both very similar. So here's what I'm going to do to relate them. I'm going to notice they both have that cosine omega t expression in them. So in fact, I'm going to rewrite both of them. I'm going to isolate that cosine expression in each one so that I can really see what's similar about them. So what I'm saying is this. Like they each have that cosine omega t plus, they each have that cosine thing, that harmonic thing going on. So I'm going to rewrite each in terms of that because I want to focus on their similarities. I want to focus on what's related about them. So I'm going to the next page, obviously. I'm going to say, well, I'm just recopying here. Okay, so I've taken one of the two derivatives, the space derivative, and I've just rewritten it. I've just re-expressed it by isolating the cosine. So I'm saying cosine omega t plus kx apparently equals the space derivative over negative a k squared, right? That's like all I'm saying. So now I'm going to go to the other derivative and do the same thing. I'm going to, the other derivative, the time derivative. All right, so I'm just rewriting, I'm just isolating whatever, solving for what he. Right? So I've just rewritten each one. Well, okay, they're each equal to the cosine expression. Well, if two things are equal to, if A equals C and B equals C, then A equals B, right? Like set equals equal to each other, whatever the theorem is. So I'm literally, so therefore I'm saying then it must be the case that right? I'm just dividing. I think you understand what I'm saying. So the space derivative over negative a k squared equals the time derivative over negative a omega squared. Well, the negative a's certainly cancel out, right? The negative signs cancel out, the a's cancel out, right? So now I go to the other page. So I'm going to the next page. So I'm saying, Right. Okay, we have like 8 minutes left. This is I could talk about this for 8 days, but 8 minutes is perfectly sufficient for right now. This thing that we just got, we took two derivatives with respect to time, we took two derivatives with respect to space, and then we just sort of related them to each other. We just sort of played around algebraically, we related them to each other. And we got that the second derivative with respect to time is equal to this simple constant times the second derivative with respect to space. This is a very elegant relationship we just got here. It may look intimidating in some ways, because in some ways it has all this notation in it that might be new to some of us in some ways. I mean, it's got derivatives, it's got second derivatives, it's got partial derivatives. One is a partial derivative with respect to time, one is a partial derivative with respect to space. But if you stand back and just look at it, we're basically saying a certain type of derivative is directly proportional to a different type of derivative. We're saying a second derivative is equal to some constant times some other second derivative. And the thing is, if you really stare at it for long enough, it's very similar to an equation that we already know, which is the second order differential equation for harmonic oscillation. What we have here, right? I mean, the second order the second order differential equation for harmonic oscillation was this. It said that the second derivative of position with respect to time, it said that the second derivative of position with respect to time was directly proportional to position itself. That's what harmonic oscillation is, Hooke's law. The second derivative of position with respect to time is directly proportional to position itself. Now what we're saying is the second derivative of position with respect to time is directly proportional to some other kind of derivative of position. It's almost is Hooke's law, just one step more sophisticated, one step more complicated, one step more differentiated, if you like. The equation at the bottom of the sheet was the second order differential equation for simple harmonic oscillation, right? This thing at the bottom of the sheet was called simple harmonic oscillation. This thing in the middle of the sheet that we just got is called the wave equation. It's saying that anything that satisfies that equation is a wave, and anything that is a wave must satisfy that equation. Okay, that equation, harmonic oscillation was a second order ordinary differential equation. The wave equation is a second order partial differential equation. The wave equation says that some kind of derivative in time is always directly proportional to some kind of derivative in space. Sorry. Okay, wait, hold on. Well, yeah, that's good. I know she's sort of joking, but no, but she's totally right. Like this thing that we just got, I mean, and this is, I mean, the point of question 11 is the point of this whole thing, is that what a wave is harmonic oscillations happening in time and in space at the same time. A wave pulse is a superposition, a simultaneous sum of time oscillations with space oscillations. That, and it can be understood as a superposition, a simultaneous sum of cosines in time with cosines in space. Or yet another way to say it is this right here. The wave equation says that what it means to be part of a wave pulse, is not just to be going up and down, going up and down. That's an oscillator, right? And it's also not just to be a picture of a wiggle. A picture of a wiggle is just that, a picture of a wiggle. A wave pulse is a picture of a wiggle, is a wiggle wiggling up and down and up and down, right? Like a wave pulse is this cosine cosining in time, or it's this cosine in time spread out and staggered in space, right? A wave pulse is a wiggle of wiggles. It's a space oscillation of time oscillations. That's what a wave pulse is, right? And I have 3 minutes. Let me put it one other way. Here's what this, that's cool. That's cool. Yes. But this is like such a great, to me, there's so much going on in this math and this physics. Like partly what I'm just saying is to have a wave pulse, you totally need to understand harmonic oscillation. Like harmonic oscillation is the fundamental ingredient to a wave pulse. That's why we're spending so much time on harmonic oscillation. But harmonic oscillation is a necessary ingredient to a wave pulse. It's not a sufficient ingredient. Like a oscillation is not a pulse, and a wiggle is not a pulse. A pulse is oscillations and wiggles at the same time. It's oscillations wiggled out through space, or it's wiggles oscillating in time, if you follow me. You got to have both to have a wave pulse. Yes, wait, I think someone just said in the chat. Wait. Yeah, Mark, right, exactly. Like literally this thing, I'm saying, yeah, exactly what you guys, yeah, worms have it. Yeah, no, yes. I mean, yes, to both of you. But here's another way to look at it with the 1 minute left. Remember, and I've got 1 minute left, so just let me say this. Second derivative of position with respect to time in physics is called acceleration. You all know that. Like d2y dt squared is acceleration along the y-axis, right? But d2y dx squared, think of a math class. Now I'm going to say this really fast because we want to think of a math class. If you just had y as a function of x, if you look at the first derivative, that's called slope, right? If you look at the second derivative, I'm talking about if you just look in space, forget time. If you just have y space and x space in a math class graph, the first derivative is called slope, like how steep the function is. The second derivative is slope of the slope. That's known as concavity, right? Right? Am I right? Yes, I'm right. So check this out. I'm going to say this in 1 minute. It's so worth it. Pick any point on some wave pulse, any point you like at all. What this equation is saying is the rate at which that point on the wiggle, like I just picked this like arbitrary point, the rate at which that point is accelerating down back to home, back to the baseline x-axis, the rate at which that thing is accelerating home is directly proportional to the concavity of the string at that point. The more bent the string is, the more disturbed, the more displaced from the equilibrium axis the string is, the faster the string accelerates back home. It's just like Hooke's law, only it's stretched out in space. Hooke's law says the farther away I am from home, the faster I'll be pulled in towards home, right? That's like the one-dimensional case. A wave says the more bent away you are from your home line, from flatness, not the farther away you are, but the more bent you are, i.e. the more concave the curve is at a certain point, the faster it accelerates toward the x-axis. A wave is a situation where every single point in space that you pick and every single time that's going on. If for any and every point in the curve, if it is accelerating at a rate back home that is directly proportional to how bent the curve is from home, that's a wave pulse. That's what that second order partial differential equation says. That's the wave equation. And you've been very patient and you're an awesome class. And I will see you on Monday and like homework and yada, yada, yada. Thank you so much. I love you all. And I say that thank you later. Yes. Thank you. Okay. Thank you. Have a great day, guys. Totally. And I'm stopping the recording. I'm going to post the thing. Oh my God. Thank you. I appreciate it. Wow. I will totally wiggle like a worm. I will. Thank you. Oh, yes. Yes. I'll wait for questions. Let me just turn off the recording, but yes, totally. Hold on. Yes. Thank you. Have a great one, guys. All right. Hold on. I'm turning off the recording and I'll wait to answer questions.